another video. I'm pretty sure as far as the slides go that have been posted, I've got everything up to the aldol. I'm working on the Claisen and the conjugate additions. Conjugate additions are not currently yet up on this slide anyway. I still actually have to draw examples of those, but I should have those probably by the end of the week. So we'll go ahead and get started. What we're looking at is ultimately the acidity of a ketone or aldehyde, or even other structures. So how does the carbonyl affect the acidity of the atoms nearby? So we're looking at the alpha carbons. So if we go through and take a look at a couple of these structures, what we're trying to do is interpret the acidity. So what hydrogen was acidic in this first structure? And you can cheat and look at the answer effectively to the right. Where was our acidic hydrogen? On the right side? We pulled a hydrogen from in here. Okay. So what we did was took those electrons, it's going to be an awful arrow, but there's not a lot of space, and we made a double bond, which then broke our carbonyl bond, gave us our enolate. The hydrogen could then come back on and stabilize our oxygen up top. Okay? If we went through to try and look or compare the acidity of, say, that compound versus just a standard ketone, so if we take a look at just a standard ketone here as an example, which of these two would we expect to be more acidic? So we actually push this around to the enol. Which of these two compounds was the most acidic? Our ketone or the diketone? What was that? They're both on the left. You can't give me that. Diketone or monoketone? So we just have the monoketone. Yeah, or the di. Which one's more acidic?
Shouldn't it be the di?
Why should it be the di?
Because you have two carbonyls drawing electron density away from
Both those carbonyls are drawing electron density away. So we could just do an inductive effect. Okay, we could say the di has an inductive effect, two oxygens, that's going to make it more acidic. Okay, we can take it actually a step beyond that. The electrons that we drew initially on the di had the electrons go towards the rightmost carbon. They could have just as easily have gone towards the leftmost carbon. Okay, why does that change our acidity? We can now push that negative charge across 3 atoms, whereas in the other case, we can really only push it across 2. Okay? So what we're looking at is kind of a stacking effect of those carbonyls. How do those affect our acidity all the way around? When we look at the diketone, with them being so close to each other, we get an inductive effect, and we also get this additional resonance effect. We can spread the negative charge from that conjugate base over 3 atoms as opposed to just the 2 if we had just one ketone. Okay, kind of makes sense?
So why doesn't it go down and pull the hydrogen off the center carbon again and make another alcohol?
So that explanation would actually kind of have to do with this structural intermediate here. Okay. Being able to pull that second hydrogen off, if we went through and did that, we would be making a double bond in here, right? What's the hybridization of this carbon, if that happens? It would be sp, which our bond angle then makes it 180 degrees. So those 2 hydrogens, we'd have another hydrogen now out there, are now opposite directions. The advantage of the structure that we've gotten drawn here is that that hydrogen can now, through hydrogen bonding, effectively jump back and forth between these 2 oxygens. If we make this carbon sp hybridized, we've now forced those oxygens apart from each other. We don't get that kind of lability of our hydrogen.
So the two oxygen actually pull towards each other?
Pull towards each other around that hydrogen. Exactly right. All right. So what we get in that product is now a very good hydrogen bonding compound, whereas before we didn't really have that ability. And if we pushed it all the way to remove that second hydrogen, we again don't have that hydrogen bonding. Okay, we would have split those apart from each other.
But that hydrogen bonding contains enough of the energy to make that more likely to happen.
More likely to happen. Okay. The other reason, what happens to your resonance ability? So in this case, let's see if I can draw this all out. Oh crap, let's just erase everything. The case that we've got drawn up there, we can take our pi electrons and move them down and shift everything entirely through. If we took off another hydrogen, let me draw that a little bit better. Would I be able to take electrons from my oxygen, push them down, and push this across? No. Why not? You don't get your p orbitals overlapping the way you need to actually push your resonance all the way through. So if we remove that second hydrogen, we actually lose the resonance ability. We can't delocalize that electric current. Okay? So we can see all sorts of reasons why that's not a very good option. Okay? And ultimately, the way we would figure that out is by drawing it out and seeing that option. And seeing that, yeah, that loses the ability to put that electron density out onto that oxygen. Okay? If we take a look at the next example, we have yet another potential to form an enol. Okay? Our enol is officially the one on the right. Okay? And our one on the left would be our ketone form, or our keto form. Typically, we would expect our keto form to exist primarily, okay, or be in that primary state. But it turns out that that hydrogen is extremely acidic, or one of those hydrogens is extremely acidic. And it can go in and push out to generate our product. Okay? Why is that hydrogen so acidic? It only has one carbonyl next to it. Take a look at the product. Where did we put those electrons from our carbon-hydrogen bond? We have an aromatic ring. We've stabilized that electron density by making an aromatic ring. So our phenol functional group stays primarily as a phenol, and we see it act as that alcohol, not as the keto form of it, because we lose aromaticity there. So when we're trying to figure out different acidities of differing compounds, what we want to do is look at those structures, look at the product, remove the hydrogen, and see what happens. How can you stabilize the conjugate base? In the two examples that we looked at, we are favoring the enol state primarily. Okay? We don't see the keto state. For the last example, we see the enol state. Okay? If we highlight that, we're looking at our enol. Okay? We see that primarily because that ene is part of an aromatic system, which now has reduced the energy of that double bond, much less so, or to a much lower energy than if we had had the carbon-oxygen double bond. If we go through and look at our first example, why do we expect the enol in preference to our keto form? Well, that enol has additional resonance with those pi electrons, putting the electron density out onto that other carbonyl. Okay? So when we're looking at acidity, what we really want to evaluate are all the possible changes that we could go through in ring. So we can look at our atom effects, size, electronegativity. In both cases, there really isn't a difference. We're looking at putting the electrons on a carbon atom in both cases. Okay? So our negative would be on what I'm highlighting now is our red carbons. Let's clean that up a little bit. How do we stabilize that anion? Well, in both these cases, we can then do resonance. Okay? That resonance will go through and stabilize the anion enough that we end up seeing the loss of that hydrogen, and we get our conjugate base. Okay? Questions about looking at these? Okay. Most of this chapter is looking at what happens after we evaluate the acidity, but we've got a reasonable amount of things to look at for acidity. So if we take a look at these two compounds, you'll notice I drew one, again, the same. And another one on the right, we're looking at acetaldehyde. Can we quantify acidity? So first off, which of these do you think is more acidic? Left or right? Left should be more acidic because? What we just talked about, just ditto, right? Okay, we have those two carbonyls. Okay, can we quantify that? Can we put a number associated with it to prove that that one is more acidic? Yeah, what do we quantify it with? We use the pKa's. What is the pKa for a more acidic compound? It is a lower value. pKa for the other one is larger. Okay? So we could go through and now start to quantify and rank things based on a list of pKa values. So if we knew pKa values and nothing about the structure, we could then decide which one was more acidic or less acidic. Okay? So we take a look at our pKa's. The one on our left is a 9. The one on our right is a 16.7. Okay, so again, we've now shown again that our left one is more acidic. Okay? Interesting kind of feature for the one on our right. We said that that was acidic. How acidic is a pKa of 16? I mean, really, when we look at the carbonyl, we didn't say anything about acidity. We looked at its electrophilicity. Okay? And in fact, it's the basicity of that oxygen. Okay? How acidic is that hydrogen? Do you have any pKa values roughly memorized? For anything? The most common one that most people have is water. It's pKa for water.
15?
It's about 15. It's actually closer to 16. It's like 15.7. Okay. We classify water as the potential for an acid, as far as acid chemistry goes. What's the acidity of our aldehyde? Darn close to a water. Okay. So we're looking at something that is actually quite acidic. Okay, so we put this in even just a mild base, that should remove that hydrogen pretty readily. Okay. Let's take a look at some unsymmetrical ketones before we even push more into our numbers. So we want to identify what's changed in each of these pathways. Okay, so how do we get to the top? What hydrogen did we remove? That topmost structure, call it our purple, or A. How did we get structure A? What hydrogen did we remove? Okay, carbon. To the left of the carbonyl. Okay, I see that now. Okay, how did we get compound B? Okay, we went hydrogen off the other side. Okay. Are those structures different? Yes. We're putting a negative charge on a different carbon. In structure A, that negative charge is going on to what type of a carbon? Secondary. In structure B, we're putting that negative charge onto tertiary. Okay. Where does an anion preferentially sit? Primary, secondary, or tertiary? Primary on an anion, because we have more electron density. So if we were trying to decide between these two, which one was the most likely to form, what might we say? Probably pick A. Let's push this a step further. Let's go through the rest of our Tautomerization reaction. What can we do to stabilize that negative charge? We can do resonance into our structure. And we end up with our endmost, and then being lazy, we can have it pick up the hydrogen at the same time. Okay. Now we take a look at our final product. Which is more stable, our product or what I've got labeled as A and B? Call them C and D if that helps. Which is more stable, C or A?
C.
Why?
No charge.
No charge. Which is more stable, B or D? D because no charge. Which is more stable, C or D? What's the difference? What's the most reactive thing in each of those cases? The pi bond. Where is a pi bond more stable? Most substituents is the favored product. Which product is more stable? D, which means which hydrogen gets removed from our structure? The red one, which is counter to our first assumption, looking at the electron density. And that has to do with where we formed the alkene of our enol. Okay? We will preferentially form that double bond in the most substituted position. Okay? Even though we might predict the stability of our intermediate to be slightly different. Okay? So we'd have to evaluate that final end result. Okay?
Why is D more stable than C?
So what's the most reactive thing between C and D? Okay, don't tell me I said the pi bond. What do you think is the most reactive thing? Okay, why the pi bond and not the alcohol?
Because it doesn't want to make more bonds.
Okay, what's the difference between the alcohol and each of those structures? There is no difference, so who cares if the alcohol is the most reactive thing? There's no difference between it, so we'd have to move on to the next thing anyway. What's our difference? Location of the alkene. Where is that double bond located? Okay, in structure C, our alkene has 3 substituents, 3 non-hydrogen substituents. In structure D, we have 4 non-hydrogen substituents. If we go back to, and I think you're right, I think it is Zaitsev. Is it Zaitsev's?
Hydrogens.
I always forget which one.
Hydrogens or something.
Oh, no, it's not on the same side. It's Zaitsev's or Markovnikov. Markovnikov is addition, so it's Zaitsev's. You're right, it is Zaitsev's. Zaitsev's rule is that we form the most substituted double bond. Which is more substituted, D or C? D. Which hydrogen was removed preferentially? Our red hydrogen, even though we formed an unstable intermediate. Okay?
So just follow the rule?
You end up having to follow your rules through and deciding where's the most important rule to evaluate. Each of these are in equilibrium. It's just a question of where that equilibrium lies. And trying to get to structure A and B, our equilibrium favors our reactant, so we go backwards. If we go through and look at the equilibrium between A and C, A and C is kind of in backwards forwards. Okay, we got a fairly reactive alkene. If we look at B and D, we've got a much more stable alkene, which means D is going to exist longer than C. So if we propagate this out over all of these possible reactions for equilibrium, we expect a much higher concentration of D than we would of C.
So is it fair to say that we can say that D is more stable because it's more hindered, so it's less likely to react? Okay.
That's the analysis I would go through. I think it's technically wrong, but I don't know why it's technically wrong. I think my analysis works just as well. And I agree with your analysis too. Same wavelength. Okay. So when we have an unsymmetric ketone, we want to pull off hydrogen from the most substituted position. That's where our enol is going to form, or our enolate is going to form, which will become relevant when we actually start to look at how we can react these enolate compounds, or these enolate structures. Okay? The next big issue is we've decided that these are now all acids, so we could go through and pick the same acid, or same structure to act as our acid. So in this case, we're looking at the acetaldehyde again, but we could use differing bases. Okay? Is using a different base going to generate a different result? Okay? If we think back to how we've been approaching a lot of the chemistry up to this point, is we really almost always say it's exclusively one direction. Okay? Before we started even chapter 20. Everything was we go one direction and that was it. One direction, one direction. That's a band, right? What are we doing this time around? We moved into chapter 20 and 22. We stopped saying we're only going one direction. We also had to evaluate going backwards. We're looking at an equilibrium. Okay, why is this going to become important? Well, let's go through with each of these bases and decide what's going to happen with equilibrium. So our first base is ethoxide. Okay, so we could use hydroxide or any alkyl oxide compound. Okay? If we go through and use that as a base, what's the conjugate acid? Ethanol, okay, or some kind of alcohol. And that's what we've got drawn over here. Okay, this is an interpretation that in theory you should have learned when we talked, or when you originally talked about the extraction technique. Okay. We can now go through and look at our reaction, both sides of it, and identify our acid, okay, or the most acidic compounds. So this one is very clearly our acid. What has to happen to do the reverse reaction? Well, our ethanol has to give up that hydrogen to the enolate. So it is also an acid. Okay? So what we've done is just identified our individual acids. The next part of this is then to compare those acids. Which one is the stronger acid? The smallest pKa is going to be the strongest acid. Okay? So how do we use that to decide what's happening with equilibrium? So this is stronger. Okay, what I like to go by is the face test. Okay? We have, let's push it to an extreme, a strong acid versus a weak acid. Face test, you get splashed in the face by one of them. Which one do you prefer? The weak acid. Okay? What is chemistry going to do? The exact same response. It's going to favor the side of the reaction that generates the weakest acid. So if we go back and now assign arrows, our stronger acid was on the right. Chemistry is going to avoid that as much as it can. So we would expect our equilibrium to favor the left. How much does it favor it? And that's where we now run into this equilibrium issue, and we don't have to quantify that, thankfully. The difference between those pKa's, relatively small. Okay? So we do see some kind of balance between the concentrations of these. We see both reactants and products. So we do see a little bit of the forward reaction, but it's not quite as much. Okay? So if we wanted to run a reaction where we had just some of the enolate, we could go through and use a relatively weak base, like ethoxide. Okay? That now gives us a little bit of the enolate and still a little bit of our carbonyl untouched. Okay? So it's really just going to depend on our perspectives on what we want. What happens if we move to, say, hydride as a base? What's our conjugate acid going to be? Hydrogen gas. You can put in the phase there. You'll notice that in this case I didn't supply the pKa's. And by I didn't supply, the textbook didn't supply them. There's a pretty good reason why. Okay, so we could go through and identify our acids and actually change my mind on the color. Let's make it stand out a little bit different. Okay, so we generate our H2 gas. And we could box in our acids, our H2, and our acetaldehyde. Why do we not look at pKa's? Why does that matter? What happens to the gas? It leaves. So if I use hydride as a base, what happens? It reacts, and then this material, our hydrogen gas, disappears. Can I do the reverse reaction? There is no reverse reaction. I favor the products. Okay? So the use of sodium hydride as a base could then say what we wanted was just the pure enolate. We didn't want any of that carbonyl compound. Okay? So we wanted to push it completely and wholly over to that enolate compound. We will look at reasons why. We'll do that in a little bit. First, I want to address this. Okay? Questions about those two? Okay, last one. Our acid is again our acetaldehyde. How do we know that's our acid? It's giving up the hydrogen, so we could look at our mechanism. We've lost the hydrogen. The other thing we could do, it's the only one that's labeled with a pKa, okay, on the reactant side, so it's got to be the acid, okay, unless we're just being really obnoxious. Where's our conjugate acid? It's our nitrogen compound on the other side. Where does our equilibrium favor now? So our strongest acid is going to have what? Biggest or smallest pKa? So we're comparing 16 to 36. Which one's smaller? 16. Which one's our strongest acid? Or 16. Face test. Which do you want in your face? The stronger acid or the weaker acid? The weaker acid. So what do? Our chemistry is going to favor our products. We're going to favor the right. Now the question, can we get the reverse? And this is where we would now go back and compare what was happening. So with our very first example, the difference between our pKa's was relatively small. Okay? 1 pKa unit. Technically, what is that, 100 times? Okay. And the next one, we had hydrogen gas released, which prevented the reverse reaction. In our last one, we now have all of our reagents, but now the difference between our pKa's 16 versus 36. What does that mean? The right is far greater favored than our left. Okay? The difference is so large between those pKa's that we effectively only make the enolate. We only see the enolate form. Okay? We won't have any of that carbonyl left over. Okay? What is that base known as? Oh, crap. I don't remember what it's called. It has some... Oh, I think I do have it. No. That was an aluminum one. Pretty sure, you might want to check me on it, it's LDA. Okay. Part of it that you're not seeing to get the L, typically it added with a conjugate ion of lithium ion. So we're looking at lithium diisopropylamine. Okay. That is one of our strongest bases. Okay. You will see that one show up more often than not. Okay. So that one does show up very commonly. Which brings us to the next question. Why would we use LDA and not hydride if they generate the exact same results? We don't want the gas coming off that. The hydrogen gas is flammable, so that could be an issue. Okay, there's another issue that really comes down to experiment. Okay, sodium hydride, very, very, very small. Okay, equally reactive, but it is so small and so ionic that its solubility in organic solvents is virtually nothing. Okay? So if I'm going to try and run an organic reaction, my sodium hydride is insoluble. What happens when I move to my LDA? What's the benefit of LDA? It is still ionic, but we have these big old alkyl groups on the side which now facilitate and allow it to be soluble in our organic solvents. Okay, why do we want things to be soluble? So that they can actually react. We're effectively increasing the surface area, allowing those two compounds to interact with each other. Okay? If it's insoluble, it's going to stay as a solid. The only place our reaction will occur is at the interface between the solid and the liquid. Okay? So our more common base to use is going to be LDA. Hydride is usually just thrown in there as an example, just to see that how we're trying to push those equilibriums. Okay? Questions about that? Okay. Woo, balance. So what can happen in these results? Okay, so it's going to depend on what we're trying to do. Okay, we could go through and use ethoxide as our base in this case. Okay, why would we use the ethoxide and not, say, sodium hydride or even the LDA? Okay, we want to make our product, we want to make the enolate. Why not use the strongest base we possibly could? Okay, think about your personal safety. Okay, we could go in and in every reaction that required an acid, instead of using just a mild acid, we could give you concentrated sulfuric acid every single time. Okay, what's going to be the problem with that?
We're inexperienced students.
It has to do with experience. It's a safety issue. If we go through and always give you the absolute strongest thing to go through and do an individual reaction, we're now exposing ourselves to more danger in each of those individual circumstances. Okay, so one of our opportunities is not just to look at which way our equilibrium favors, but then also to decide to use the maximum effective or the minimum effective strength that we would need. So why in this case would we get away with using ethoxide to favor our product, where in the other case, ethoxide actually didn't favor our product, it favored our starting material. Okay, we said it effectively went backwards. Why can we get away with using ethoxide in this case? The acidity of our carbonyl-containing compound is much, much lower, higher, much more acidic. Let's just stick with that. Okay? Why is it much more acidic? We could go back and use a resonance effect. We have that secondary carbonyl. Okay? That makes our hydrogen relatively much more acidic. In fact, it cuts the pKa roughly in half. We go from a 16.7 to a 9. Okay? We're now in the realm of a phenol as far as acidity goes. Okay? So why bother to use a hydride or something like that if I can get away with using something that's much weaker, it's going to cause less hazards to me, and then if we propagate this even further out into the whole realm of chemistry in general, there's a big push for green chemistry, which means don't use dangerous stuff. Okay? Avoid it as best you can. So in this case, it just doesn't make sense to use hydride or LDA because I don't need to use it. If I don't need to use it, I shouldn't use it. Okay? Figure 22.2 allegedly summarizes all of these relevant factors. There's a big question mark there because I couldn't find it. Granted, I was using the digital book, so I couldn't flip through it as easily, but I couldn't find that figure, so I'm not quite sure what they were talking about. Okay? It might indeed be there. It's in theory their slides, so they should be right. Okay? So what we're looking at is evaluating the pKa of your acids and then also the strength of the base. Okay? As far as the bases that you can use, we're really looking at 3 types: ethoxide, hydride, and LDA. Between those two, it's really ethoxide and the LDA that you're going to be dealing with. Okay? And again, it's going to depend on what circumstances or what you're trying to do in each of those cases. Okay? Questions about that? Okay. So we got a general summary here. Okay. How can we convert a carbonyl compound into a nucleophile? Well, what we're going to do is add a base. When we add a base to our ketone, we can remove that hydrogen by the use of our strong base. Can attack the hydrogen. The electrons can then go onto our carbon. Okay. And we can either form the enolate or the enol, depending on what conditions we're under. If we're using a strong base, we're looking at forming the enolate. If we're under acidic conditions, we can still form the enol-like or the enolate type compound, but we end up forming the enol. Okay, why do we get the enol under acidic conditions and not the enolate? We have to protonate that oxygen. We're under acidic conditions. The oxygen in the enolate is basic. Okay, so under acidic conditions, we're going to have to protonate that. Okay? Which atoms are our nucleophile? When we look at our enolate, what is a nucleophile? What is the definition of a nucleophile? Okay, we're looking at a negative charge. Okay, we're looking at an electron donor is a nucleophile. So which atoms can be our nucleophile? Okay, right idea with the pi bond. The issue is I asked which atoms. We've got the oxygen and then we have a carbon. Which carbon? How do we decide?
Well, the one connected to the oxygen is going to be more positive, so it's the other one.
That's one way to do it. The other way to do it, if you draw your resonance structure, you get a negative carbon on the outside. So we are marking two nucleophiles when we go through and identify our enolates. Okay? Between those two, which one's more nucleophilic? Do we expect our carbon to be the better nucleophile or our oxygen? Our carbon, which is the other big driving force that or the other big thing that we're using in this chapter. Once we make the enolate, we now have a carbon nucleophile. The carbon will react preferentially because it is less electronegative than the oxygen. Okay? The rest of our chapter is now going to look at a whole bunch of different electrophiles. Okay? So those electrophiles that you guys have seen, we'll look at halogens, we'll look at alkyl compounds, we'll also look at carbonyls, and then I didn't quite know how to label this, so it's sort of grouped in with the carbonyls. You notice that S is a slightly different color. I know, very, very subtly different. We will look at alpha beta unsaturated carbonyls. What does alpha beta unsaturated mean for a carbonyl? How would I draw a carbonyl? Carbon oxygen double bond. Where's the alpha position? Right and left. I'm going left because I got more space. Where's the beta position? Next carbon. If it is alpha beta unsaturated, what does that mean? It's missing hydrogens, but we can't just remove hydrogens. We've got to replace it with something. We're looking at a double bond. Okay? So the very end of this is the slides that I'm still working on trying to get put together are the alpha beta unsaturated carbonyls. And we'll also use those as electrophiles. Okay? So we've got 4 primary categories to go through and deal with. Carbonyls can get separated into further categories because we can see a carbonyl on a ketone, we can see a carbonyl on an aldehyde, we can see a carbonyl on an ester, or for that matter, even a carboxylic acid. So we've got a whole bunch of varieties of carbonyls that we can work with, and we're going to start to look at a few of those. Okay? So to start off with, we'll pick one that we're a little bit more familiar with, our halogens. Okay? So if we start with our ketone under acidic conditions and we react it with bromine. Okay? What did we just say bromine was going to act as? An electrophile. How does bromine act as an electrophile? Because if we draw out the Lewis structure for bromine, what do we get? A whole lot of electrons around each of those bromines. How do we get an electrophile out of that? So what ends up happening is we can polarize the bromine bond. Okay? When we looked at the EAS chapter, we looked at 2 possible ways to polarize it. We could use iron tribromide to polarize. Light is going to break it into radicals. Okay? So we could have used iron tribromide. The other one was acetic acid. Acetic acid works because we bring in H+. As soon as the electrons get near that H plus, what happens? Now this bromine has lost electrons, so what does it do? Panics and steals them from its brother. What's left over? Our electrophilic bromine. Okay? So our halogens can indeed act as electrophiles. They're very large, very polarizable. We're allowed to push that electron density around. Okay? So I'm going to erase all that because I want to deal with the rest of this. Let's go through and look at how we can make our enol, so our active nucleophile. What's the first step of our active nucleophile going to be? Okay, and remember, we are under acidic conditions. So I'm hearing attack carbonyl carbon, and I heard a protonate. What do you mean by attack? Get a little bit.
What does the nucleophile do?
What's attacking the carbonyl carbon? Okay. What I like to do again is pull a face test on this. A carbonyl, acid, bromine. Which of those do you know you're going to not like have splashed in your face? The acid, for sure, you don't want splashed in your face. That's going to melt it. The reason why you don't like bromine is the secondary hazards you have actually looked up and know something about. But let's assume you don't know anything about that. Okay. Then the acid's going to be our issue. What makes the acid most reactive? It's charged. What's its charge? What do we need to stabilize positive? Negative. Where do we have negatives? We have got the Br, but we said we want to evaluate our enol first. We can look at our oxygen. We're going to pick the lone pair and not the pi bond only because that's the way Sapling's got this set up when you try and go through and do mechanisms. Remember when we talked about it before, they are effectively the same thing, using the pi bond or the lone pair. You generate the exact same product, you're just generating different resonance structures from each. Okay? So what's the result of that arrow pushing? Did we do anything to the ring? No. Did we do anything to the pi bond? Did we do anything to the pi bond yet?
Not yet.
Not yet. What we did was took a lone pair on that oxygen and we shared that with our hydrogen. Okay. Notice where the arrow is starting. The arrow is starting at the lone pair. It does not show the pi bond. Okay. The only reason I'm pushing this is that Sapling, if you go through and use the pi bond, you will get it wrong. If you use the lone pair, you will get it right. Okay? They are the exact same thing. Okay? Is this the correct structure? What's wrong with it? Oxygen needs to be positively charged. Okay? Does oxygen want to be positive? Nope. So what can happen? So we can break the pi bond.
We can't do that in one step.
Within Sapling, no. You cannot do that in one step. Okay. So what I would do is break that pi bond and show the resonance structure. Okay, because ultimately I think you guys need practice with the resonance, so I will draw it. We've got our positive charge now on the carbon. Okay. Does that carbon want to be positive? Nope. So what does it do? If it did the bromine, what did our carbonyl compound act as? An electrophile or a nucleophile? An electrophile. What did we say our carbonyl needed to act as within this chapter? It's a nucleophile. We're concerned about the alpha carbon chemistry. Where can that positive charge get electrons that's even closer than bromine? We can look at the hydrogens that are off on the alpha carbon. We can take those electrons. Let's show that in red. And we can then get to our enol state. what can happen now? And Josh, you've been wanting to say it the whole time. Now we can have our halogen come into play. The electrons from our oxygen can be shown to come back down. We attack the bromine with our pi bond. The electrons shift onto the other bromine. The result is this guy. Whoops, that was problematic. Let's try that again. Positive charge on our oxygen. Does oxygen want to be positive charged? Nope, so what does it do? Take them from the pi bond is the easiest, but it could also take them from the hydrogen. Where do we end up? With our final product. Okay.
Does the oxygen take them without any?
Why did I not show something pick up that hydrogen?
Because we're using acidity.
So it's under acidic conditions, so if we said it was a base to remove it, we'd have a problem because we don't have base, we're under acidic conditions. So it's going to be anything remotely basic, so anything with a lone pair. We could be looking at the solvent, we could be looking at bromine, we could be looking at another oxygen from a starting ketone. Okay? More than likely, when we run this reaction, we're actually looking at water. Where did the water come from? From the workup. Remember, every time you run a reaction, you mix your chemicals, and then what do? You stop the reaction. You quench it. How do you quench it? One of the more common methods, you add it to water. That water can help you finalize those last acid-base positions. Okay? Which is a bit obnoxious, but that's how mechanisms are done.
So on the test, what do you want us to show?
What I want you to show are the red arrow. I don't care what base you use, if you even want to use a base. What I want to see is that you know that that oxygen needs to get electrons. The easiest place for it to get electrons and progress forwards is from that hydrogen. Okay? Which is why I didn't show the base. Okay? But I know a lot of people don't like seeing or don't like it when I do that. Okay? This process is known as autocatalytic because we regenerate the acid. Okay? That hydrogen ended up getting pulled off, and so we again have H+. Okay? So as we run the reaction, we end up generating more acid to be able to protonate and continue this process. Okay? So we get the tautomerization first, then we get the halogenation reaction. Okay? Questions about what's shown? What would happen if we did it under basic conditions? Cheat and look at the structures drawn above. What happens when we do it under basic conditions? It's the difference between your acid product and your base product. Nothing. You get the exact same product. So what's the difference? It's all going to be with the mechanism. Okay, let's see. Did I leave space for it? Okay. Whoa, that's weird. Ah, don't look at that. Sorry, that was a different section. Okay. We'll switch it to the base product in just a second. So still under acidic conditions, what happens if we have an unsymmetrical ketone? Where do we expect that bromine to go? Markovnikov isn't going to work in this case. You're thinking Zaitsev's to form the enolate. Where does the enolate form? So that doesn't even put on the bromine yet. Where does our enolate form? Where do we form the ene?
The least substituted. We put the negative on the least, on the secondary carbon versus.
We put it on the most substituted. Our ene forms our most stable double bond. So we would form this for our enolate. Let me try that again. So this becomes a single bond, and we get our double bond here.
For your product.
So that's the enol. Now the enol can react with the bromine. So what happens? The double bond comes out, reacts with the bromine. Where does the bromine substitute? Substitutes at this position. How did we get it onto the other position? We said that the double bond would have had to form over here. So which is the favored enol, red or purple? The red, because you formed the most stable double bond, the more substituted double bond. Okay? So that goes back to our unsymmetrical ketones. We always want to form our most substituted enol. The more substituted it is, the better off we are, the more stable. Okay? Now that we've got that formed, now it can react with our bromine, and what ends up happening? We see the bromination occur at our more substituted position, and we get our major product where our bromine is on that tertiary carbon, and our minor is where it's on the secondary. Okay? So we have to kind of watch out for that chemistry. Yeah.
This is where I think I got what was called what. So this product here is the enol. And what do we call this intermediate then?
An anion?
Just an anion?
Yeah, the or a conjugate base.
The enol.
And so what we're deciding with that slide, so that was 3 or 4 slides back. I might regret this.
No, you don't have to do that. I got it now.
Wow, that was way back there. What we're looking at is what we already talked about. Where does our enol form? Okay? And we talked about looking at the conjugate base, but that's ultimately super reactive, so we need to look at the first stable intermediate. And we called this D and C. Between those, which was more stable? D, because we formed the most substituted double bond. The more substituted our double bond, the more likely it is to form. If it forms, then it can go on to react. If C never forms, it doesn't matter if it's less sterically hindered. If it doesn't form, it can't react as an or as a nucleophile. Okay? And so what we're doing is propagating that information through to the actual chemistry that occurred all the way here. Okay? And so what we end up seeing is our major product puts the bromine at the most substituted position. Okay? And it all has to do with our enol. Our enol is more stable where we have the double bond at our more substituted position. Okay? What happens if we switch it up? Let's see if this actually worked. Oh, never mind. I was thinking of something else. So it also says that a mixture of products is generally unavoidable. We do favor the bromine at the most substituted position, but we do have some of that other enolate available, which means we do get some of the bromine going to the other position. Okay? And that's what this statement is saying. We get a major product, but our yield is going to be lower. We would never expect 100% yield because we do get some contribution from our minor product. Okay, so we're just saying we can't completely remove that product. Okay. What happens with this next sequence of reagents? Step 1 is going to do what? What's that? Yes. Okay, that's what I wanted to hear. It gives us one of the products. Which product does it give us? Okay, we're going to get our major product out of this. Next step. Step 2. What is pyridine? There we go. That was exactly it. Pyridine is a base. We're looking at a nitrogen-containing compound, and because I'm always bad with the circles and nitrogen compounds, I'm probably going to draw it wrong, but I think what we've got here is pyridine. Okay, so we have a base. What is that base going to do? Where is it going to take the protons from? Okay, an acidic one, so we could try and do the alpha carbon, but then we do that resonance with an enolate, okay, or that Tautomer with the enolate, and this is not a strong base. So we end up preferentially keeping our ketone. Is there another acidic hydrogen? It's not the alpha carbon. It's actually going to be the beta hydrogen. Why is that hydrogen acidic? What happens if we remove that hydrogen? So our base comes in,
You get the least substituted protein.
removes the hydrogen, and we end up with now a lone pair on that carbon. Negative charge. Does it want to be negative? No. So what does it need to find? Positive. Is there something positive nearby? Say a carbon that has an electron withdrawing bromine on it? What happens now? How many bonds does this carbon now have? Too many. Do we have a weak polar bond that we could break? And we have a good leaving group. The result we end up ending with actually our alpha-beta unsaturated ketone. All right? So what this reaction, I don't know why they threw it in the textbook as making this some fancy extra thing. Okay? It's ultimately step 1 is this chapter, 22. Step 2 is your elimination chapter, which I haven't used this textbook. Chapter 7, 8. Okay? First semester. Okay? So what they're asking you to do is actually start to put together now multiple chapters to propagate out to your potential products. Okay? I don't like the face. What does that mean?
Confusion.
Okay. You want me to draw it again? Should we do the full mechanism?
So weird.
Aware means we're doing the full mechanism. Okay, so let's do this chapter's material and first semester material? Absolutely. So we are starting with
I got the first part.
your ketone. Okay, so the first part you're happy with, step 1. Okay, so step 1 was our H plus and BR, BR2 actually. Is everybody happy with the first part? I am accepting that as an answer. We have our bromine. So there's our first part. We then go through and do step 2. Step 2 was our pyridine. This is where your ACS test can get a bit obnoxious too, is they might just say pyridine. How would you know what the structure was?
Look at the answers.
So you could hope that you looked at the answers and saw that one of the products lost a hydrogen or something along those lines. That's a bit dangerous. Okay. Other option is, I'm pretty sure, though not positive, if they're going to provide you the name of some complex solvent, that they give you the structure at the very beginning. So if they say pyridine, flip to the beginning and look through their arrangement of atoms, and they might tell you what pyridine is. Okay. Hopefully they do. If they don't, shot in the dark and see what happens. Okay. So pyridine, as Angie suggested, was what kind of a compound? A base. How do we know it's a base? We've got the lone pair on the nitrogen. And it's sterically hindered, so we wouldn't expect it to act as a very good nucleophile. Okay? So we now have a base. So if we've got a base, what do we need to react it with? An acid. Okay.
There's nothing you liked and we just reacted with another alpha.
So let's take a look at our hydrogens here, our alpha hydrogens. That is absolutely a valid step. Do I need to show the arrow for that? Mechanistic arrow? I'm going to leave it up. I'm going to try and put it off to the side. So we would end up with our bromine, and we would have the negative charge on that carbon, right? Okay. That carbon can do the Tautomerization. Whoops, let's have that pick up the hydrogen right away. That's an eraser, not a pen. Very, very lazy. Can't say I recommend you do that, but. And we would end up with our enol. To form the enol, What did we say was happening? Is this a one-directional reaction? That was an awful way to say it. It's in equilibrium. Okay, the equilibrium favors the ketone every single time. The only way we get it to favor the enol is if we use a wicked strong base. Is the pyridine a wicked strong base? No. So that when we look at our arrows, these are not unidirectional arrows. These arrows actually do this. Do we form much of that enolate or the enol compound? No. We form a very, very small amount, not enough to suggest that we actually have the product. Okay? So that is an acidic hydrogen. It just, unfortunately, we don't generate enough of it to actually say we get a product. Okay? Because our equilibrium doesn't favor it. So what we would have to do then is say, do we have another acidic hydrogen somewhere else within the structure? Okay? And that's, again, we just evaluate every single hydrogen within that structure and decide, is it more or less stable? We should see two possible hydrogens to remove. A hydrogen here and a hydrogen up here, actually, technically. Okay, so we'll look at those products again as possibilities. If we remove the hydrogen, or blue hydrogen, what we end up with is our negative charge up on that carbon. Does that carbon want to be negatively charged? No, so it needs to find something relatively positive. Where's the closest positive to it? The carbon to which it's immediately attached. Why is that carbon positive? Because of the bromine that's attached to it. The electrons can come down and we kick out bromine. What's the result? Okay. What happens if instead we use the purple hydrogen? We got that negative carbon again. Is that negative carbon good? No, not happy. What does it do? Tries to find something positive, which is that carbon next door, and we kick out our bromine as a good leaving group. The result, is we end up with that as a product. Our red product we said was bad because we form it in very, very small quantities. Between the blue and the purple, which one's better? Purple because we form the most substituted alkene. Okay? Make sense? Other questions on that? Are you still trying to get it drawn all? No? Okay. Just checking. So we can end up generating our alpha-beta unsaturated ketone. Okay? So it's a good question that you brought up. This is going to be one of the problems that you're going to continue to see. You're going to have now not one option, but 2 or 3 possible options. You have to decide between those 2 or 3 possible options which one takes you to the correct answer. Okay? That correct answer may be difficult to interpret. It may be that you lead to a dead end where you just can't stabilize it. Okay? And you get an anion and you can't figure out some way to stabilize that negative charge. Or you'd have to know a bit more with that chemistry, and we realize that we've got an unfavorable equilibrium. The unfavorable equilibrium cuts that off as a product. Okay? So this is, to me, where things both become really interesting and really difficult, because you should end up drawing, just like we did, 3 possible products. And then evaluating each of those 3 possible products and saying which of those is the most likely. Okay? So that's where it becomes fun, because you now get to predict a whole bunch of different things. Where it becomes obnoxious is you have to predict a whole bunch of different things. Okay? Or you have to decide among those which one's the best. Okay? We can go through and do a special case of alpha halogenation. This is the Hell-Volhard-Zelinsky reaction. I'd be surprised if you ever see a question on this. I had never heard of it. You'll notice that our conditions are slightly different than what we saw before. Why would the conditions change?
Carboxylic acid.
We're looking at a carboxylic acid functional group instead of just a carbonyl. Okay? So that's going to change the dynamics on how that carbonyl can interact and do its job. Okay? If this was just going to be a standard carbonyl reaction, we would predict that we remove our hydrogen from over here, we form our enol, the electrons can come back down, and our second step, come back out, react with our bromine, and we put the bromine on, there's our product. Right? So standard reaction as far as we're concerned. Okay? It's a little bit more complicated than that. I'm not too concerned that you're aware of that extra complication. What I really am concerned about is that you see the carbonyl, you see that that bromine could potentially go on there. Okay? Why is the chemistry a little bit different? What else did we add? I don't see hydrogen being added. Water's being added as a secondary step. We are, oh, I see, hydrogen as the acid, the carboxylic acid, but we actually needed that in our previous reaction too. So that could even help facilitate this. What's the other big difference? It's a hint, it begins with P. Our phosphorus tribromide. Have we seen that reagent before? Okay, or we could try and rephrase it. Do you remember seeing that reagent before? What did it do? It did a substitution reaction. We substituted an alcohol for a bromine. Okay? So the first step of our reaction is actually to turn the acid over into the acyl halide or acyl bromide, blah, 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 out the other end of it. Okay? That bromine actually makes this hydrogen now even more acidic because that bromine is electronegative, and we don't get a resonance stabilization with our two oxygens. So now we can remove that hydrogen and do our bromine substitution in that position. So we end up with our alpha position with the bromine. Okay? That's darn close to our product, but we still have an OH there. How do we get the OH? We add water. What's special about water? It has electrons, can act as a nucleophile, or at the very positive carbon, kick off the bromine, and we regenerate our acid. Okay? So for all intents and purposes, we are doing the exact same thing with our alpha halogenation, except this time around, we have to use the PBr3 to effectively deactivate the carboxylic acid functional group and get that chemistry out of the way so that we can do the bromination that we want to. Okay? So it's kind of interesting in that respect, but it's not all that exciting. Again, you probably won't ever see that again. Okay? And we just talked about this. So our formation of the enolate is not favored initially, but what we're looking at is our equilibrium getting pushed forward because of our second step. Okay? Removing the bromine at the very end and putting on our acid. Okay? If we put on the bromine instead of the OH, should it become more acidic or less acidic? Whoa. Wait a second. This is an entirely different problem. Somehow or another, I did not see that. I don't know why. That was weird. Okay, sorry. I was talking about the wrong thing. When we put on that bromine initially, it becomes more acidic in our Hell-Volhard carbonyl process. Okay, so ultimately all you need to know is that you're still doing that alpha bromination. Okay? Next slide, if I look at it a little bit more carefully on what we're talking about, now shifts to going under basic conditions. Okay? Under basic conditions, we're still doing effectively the same type of chemistry. We go through, we remove the hydrogen, we form our enolate. Should we expect this one to be more or less nucleophilic than our enol? what does our enol look like? I like the enthusiasm. Enol. Which structure is more acidic? Our enol or the enolate? Or sorry, more, what was I saying, nucleophilic? Why the enolate? Because it's negatively charged, okay? That becomes a really important feature under our basic conditions. Why is that going to change our chemistry? Well, once we've made the enolate, it will react much more readily with our bromine and put that bromine on. What's the problem now with that alpha carbon? What else is attached to it? Another hydrogen. Okay, well, if we go all the way back to the beginning, our first hydrogen, why was it pulled off? It was acidic because the enolate stabilization. If we now go to our very end, our red hydrogen, is it acidic? Do we have an enolate to stabilize it? Yeah. So it is still acidic. Is it more acidic than our blue hydrogen? Why is it more acidic? You have an inductive effect of that bromine pulling electron density away. That hydrogen becomes even more acidic. So what is more than likely going to happen? We'll do the reaction again. Okay. This is the problem with our problem, and we can use it to our benefit with basic conditions. Once we put on that first bromine, we made it even more acidic. We can actually propagate this out to putting on more bromines. So we can do multiple substitutions this way. Okay? So that's the issue with our bromine. If you go back to our summary slide under our acid and base bromination reactions, I underlined the basic so we could see it, and then right underneath that underlining, you go back to the video, it says multiple substitutions. Okay? And that's because we've made that position even more acidic. Under the strong basic conditions, we're going to end up pulling off that second hydrogen. We're going to get another substitution. Okay? So that's an issue with our basic situation. So we do not get monosubstitution. It is not possible because of that extra acidity of that hydrogen. As soon as we make it once, and we now have a solution, okay, we have a ton of our ketone and now a ton or one molecule of our brominated compound, that brominated compound is going to react before the ketone. So we'll end up getting the second substitution before our ketone reacts. Yes?
There was carbons on the other alpha. What did you get at both sides?
We would get the bromination happening to both sides. So why do you think we put the carbons there? So that we didn't have to draw them all out. Okay? But yeah, if there were hydrogens there, we would still have to do the brominations out on the other side of that too. Okay?
Did we get more than
What's that?
substituted?
What's that? More than?
More than 2 bromines?
Yes. That is actually this last reaction, which I'll talk about really quickly. If we have a very special case, so to get more than 2 substitutions, we have to have something known as a methyl ketone. Why is it a methyl ketone? It's a ketone next to a methyl group. Okay? So to get more than 2 substitutions at an individual carbon, we'd have to have a methyl. If we have a methyl ketone, now all of those hydrogens are potentially acidic. And so what ends up happening is we get 3 bromine substitutions. Okay? And that's what makes this chemistry really, really interesting, because what's the end result? Oh, I covered it up. Your end result, we'll talk about why it's this, the answer for this reaction is the carboxylic acid. Where did all the bromines go? They left. Our intermediate before, at the end of step 1, actually, we don't really have an intermediate at the end of step 1. It's actually that compound. Right before we form the acid, we form CBr3. Okay? That is a very special species. 3 bromines means we've pulled a lot of electron density away from the carbon. What does the carbon decide to do? Steal electrons. It will steal electrons from the other carbon. We've generated a pretty good leaving group. We still have hydroxide floating around in the solution. The hydroxide can come in, do our substitution, and what we end up generating, very fleetingly at this point, this species, and I'm going to call you out because you were at Scottsdale. What is that species known as?
I don't remember.
Anybody remember what this species is known as that I got circled? Carbene. Oh wait, is this the carbene? No, never mind, it's not the carbene. Okay, it's just a really good leaving group. Okay, so we've got that really good leaving group. That carbon is negatively charged. It can pull off the hydrogen, and we end up with the, okay, we follow that up with the next step of adding the acid, and we end up with our final compound. Okay, we will pick up there doing that exact same reaction a little bit neater, which doesn't say much because that's pretty awful. I'll do that a little bit neater on Monday. Okay?
Still exist.